Today, let's discuss limits. First, we're going to go ahead and talk about what a limit is and its notation so that we understand what it's asking when we see something. So, a limit is a value that a function f of x approaches as its x value gets closer and closer to a specific number. Note that I'm not saying what the actual f of x value is at x. I'm just saying what happens as x gets closer and closer, right? We use this little arrow notation to mean approaches. So for example, here I have a limit written here. I have the limit as x is approaching 2. All right, so there's my little approaching. X is approaching 2 over here of x squared minus 4 over x minus 2. Again, what that means, this is my f of x function here, is I want to know what does this equation, this graph, get close to as x approaches 2. Okay, again, I don't care actually what's happening at 2. Right, now different ways that we can take a look at this are both numerically and graphically. So we're going to start with numerically. Okay, so to do it numerically, we're just going to sit and use a calculator to help us do this. So we're going to use our table in our calculator to input values that are close to the point that we're interested in. In this case, I want x to approach 2. So I am going to plug in numbers. So here I have a table set up ready. 2 is right in the middle there, and I'm choosing numbers that are getting progressively closer and closer to 2. So 1.9 is pretty close, but 1.99 is even closer. 1.999 is even closer than that. So that's how I'm choosing those numbers. Similarly in the other direction. Okay, so let's pull out our calculators to do this. So we're going to go ahead and type this equation into our calculator, x squared minus 4 over x minus 2. So let's go to y equals, we've got in parentheses, x squared minus 4, close parentheses, divided by, open parentheses, make sure you have parentheses correct, otherwise you're definitely plugging in the wrong equation. Okay, there is my equation. And we are going to go to our table to take a look. Okay, now notice at 2, I can already see this error here. Okay, so something's weird happening at 2. And our table by default tends to be set in integer values. Okay, but we can change that. Go to second window to go to table set. And instead of having it do auto, we're going to move it over to ask. Okay, that will mean that we can then choose which values we want our calculator to give us in our graph. Okay, so when I come to this, now it's all empty and I can type in the numbers that I want. So earlier we chose 1.9 and then 1.99, progressively closer. So I'm going to go ahead and type 1.9 for the first one, 1.99, oops, I lost my point, 0.99, 1.999, and then 2, and it's giving me the appropriate y values that go with those. On the other end, we had 2.001, 2.01, and 2.1. Okay, so let's go ahead and write down these values. I've got 3.9, 3.99, and 3.999. So we'll put them in here. So my f of x function, which again is this equation here that we're plugging x into, is 3.9, 3.99, 3.999. When it gives me an error here, what does that really mean? Okay, it means that my function is undefined at that location. Okay, error is never an appropriate thing to say. Okay, and then 2.01, 001. Let's see, what were the other values? 4.001, 4.001, 4.01, 4.1. Okay, so once again, our limit is defined as x gets closer and closer to 2, so here I see x getting closer and closer to 2 here from both directions. Okay, what f of x is approaching what? What value is f of x approaching? So we can see here pretty easily from our table that as we get closer and closer to x, my f of x values are getting closer and closer to what from each side? Okay, so this kind of squishes in between to see that in here, the value in between is 4. Okay, so this limit even though the actual value itself is undefined, this limit is equal to 4 because my table, my graph, my f of x function is approaching 4 from both sides. Okay, now, in addition to this general limit notation, we actually have this one-sided limit notation. One-sided limits. Okay, the notation is very similar. I have the limit as x is approaching 2, but I'm going to have this little negative sign right here. Okay, that little negative sign tells me that I want the limit from only one side. The negative means that I'm approaching from below, quote unquote. So approach from below. And when we say approaching from below, we're really meaning from smaller x values. Okay, similarly, I can also have the limits as x is approaching 2 from above with little plus signs. Okay, so again, that would be approach from above instead of from below, aka we're looking at larger x values. Okay, so if I wanted to find my limit from below, that limit from below would be again using smaller x values, so I would only look at this side. Okay, this side is the only side that I would look at for from below, whereas from above, I would only look at this side. Okay, in this case, each of these limits is also equal to 4. Now, that's not always going to be true. They're not always going to be the same. Okay, so let's take a look at some other examples. So here I have a bunch of examples. We're not going to do all of them, but we're going to take a look at a few of them. All right, so the first one I want to look at is number 6 over here. 6 is my limit as x is approaching 1 of this weird symbol thing as x minus 3. Now that weird symbol is our step function. We talked about it earlier in the year. Okay, the step function, remember, is like the greatest integer that's less than or equal to the value that's there. Now this can also be graphed in our calculator, so again we are going to use our calculators to help us with this at the moment since we're still doing it numerically. So let's go to our y equals. If we are graphing this particular one, then the function that we want to use is actually the int function, int for int. The int function is under math, and then we move over to number, go down to int for integer. Right? Oh, that was not int, that was min. Math, num, int. Okay, so I've typed in the int function. X minus 3 is the function that's on the inside, so I have x minus 3. Right, and so just as a reminder of what this looks like, that is our little step function. We have lots of these little steps. That's why it's called a step function. Okay, so again, we are going to do this based on using a table. Now earlier, we chose our values for our table to be approaching 2. In this case, what should our values be approaching? Since this is approaching 1 down here, we want to make sure to approach 1. Okay, so that means the values that I would choose in my table set is still based on asking. So I don't want these values anymore because I want this one in the middle to end up equaling 1. So I have to choose values that are less than 1 that get progressively closer to 1, and then the values that are greater than 1 that get closer to 1. So less than 1 would be like 0.9. So let's change this to 0.9, 0.99, 0.999. And then at 1, and then we have slightly larger numbers, 0.01 and 1.1. Okay, so these are now the values for this particular graph. So I'm going to go ahead and write down that little table here. I've got 0.9, 0.99, 0.999, 1, 1.001, 1.01, 1.1. And from one side, looks like -3, -3, -3. And the other side is negative 2, negative 2, negative 2. Okay, so now when I'm doing this, again, earlier we talked about these one-sided limits. In this particular case, I want to take a look at those one-sided limits. The limit as x is approaching 1 from above of x minus 3. Above, remember, means from larger values. And I want the limits as x is approaching 1 from below x minus 3. Okay, now from below, remember, we're looking at values that are less than. So these are the values that are less than. Okay, again, I want to talk about what's approaching, not what's actually there. So you may notice that all of these numbers that are less than x equaling 1, all of those y values are negative 3. So this first limit from below is negative 3. Again, it doesn't matter that the negative 2 there is different. I want to know what's happening as I get close. And as you keep adding 9s, 0.99999, 0.9 with like 100 nines following it, that's going to stay as 3, negative 3. And so that limit is negative 3. Again, it doesn't matter that at 1, I have a different value. Now, from above this limit, I'm looking at numbers that are bigger than 1. And notice I'm not circling 1 in there because, again, I don't care about what's actually at 1. Bigger than 1, that one-sided limit is equal to negative 2. Okay, now you may notice that these two numbers are different. When they are different, then the limit itself actually does not exist. Okay, so this answer for number 6, this whole answer, is equal to does not exist because these two one-sided limits don't actually equal to one another. So to represent that same idea graphically, let's take a look at a pretty interesting graph here. So here I've asked for a number of one-sided limits and also the limit itself. Okay, now again, numerically, I would plug in numbers that get closer and closer to this particular value, x value, and look at what the y value is approaching, either from above or below. And if these two one-sided values are equal, then I have my general limit. The whole graph approaches a certain number. So let's try some. Here I have the limit as x is approaching 1 from above. Okay, so from above, remember that means greater than 1. Here's 1. So I have x values that are bigger than 1, so that's like on this side over here. And I'm plugging in these x values as I get closer and closer to the value of x equals 1. And I want to see what those y values are doing. So if I choose like a random point over here, okay, that y value is, looks around like 3.75-ish. Okay, but as I get closer, okay, let's choose another value that's closer. Okay, and then closer, and closer, 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 where am I approaching? My y value is approaching 4. Okay, whereas from above, oh, that was from above. From below, the limit as x approaching 1 from below means that I want to look at y values that are less than 1 and go towards 1. So I'm looking on this side of my graph. And again, I can choose some random value and say, oh, well, that y value looks around 3.75 again. And then again, I want to get closer and closer. So I'm choosing these values that get closer and closer. And that y value also looks to be approaching 4. Once again, if these two values are the same, then my full limit without the little plus or minus is just equal to each of those. If they're different, my limit does not exist. If they're the same, then that is what my limit is equal to. Okay, so try this for the next bits. Fill in the rest of what is here. For limit as x is approaching 2.5, here's 2.5 right here. From above is coming from this side, so that looks like it goes to 0.5. From below, that's coming from this side over here. That looks like it's also going to 0.5. And so since those both exist and they're equal, my full limit is 0.5. As x is approaching 2 from above, here is my value of 2. Above, again, larger x values. So here are larger x values on this side. So it's going this way. That is approaching 2.5. From below means smaller x values. So these are my smaller x values. So it's coming from this side. So that is approaching 3. And these two are different values, which means this limit does not exist. All right, and this last line, I have the limit as x is approaching 3 from above. Here's 3. Above means on this side, so I'm going this way. I see it going up, 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 up to infinity. Now on any AP test, they don't actually use infinity. They just use does not exist if infinity shows up. But for me personally, I want to know that you understand what the graph is doing. So I would prefer that you write infinity. Okay, from below, that's from this side. That's also going up to infinity. Okay, so since they're both going to infinity, for me, again, you would write that my limit is infinity. For the AP, for all three of those, you would write that it does not exist. Okay, so I've already kind of mentioned this before. A limit exists if and only if, that's not an extra F on accident, if and only if both one-sided limits exist and are equal. So again, they have to exist and they have to be equal. Now, just as a note, as we were working through this, you may have been like, well, isn't there this point down here? At x equals 1, my f of x value is totally equal to 2. Why doesn't that limit show it? Because again, remember, your limit doesn't matter where it's actually at. The y value at the point doesn't matter. It's just where do the y values approach as I get close to that x value. So let's find a few more limits. Go ahead and find each of these limits. Again, first find the one-sided limits and check whether or not they are equal. If they are, then you have a limit. If they are not, then you do not have a limit. Take a moment to do that. All right, so the limit as x is approaching 2, again, I'm going to look at 2 from both above and below. So as I approach 2 from above, I am going towards 1. And as x is approaching 2 from below, all right, so as we're doing limit as x is approaching 2, we do want to look at both this one-sided limit. So I have the limit as x is approaching 2 from above of f of x. From above, there's 2. I'm going from that side, larger x values. That's going to give me, this point goes towards 1 here. All right, and from below, the limit as x is approaching 2 from below of f of x, that comes from this other side, this side over here. And so that also looks to be going up to 1. So since they both go to 1, then my full limit is equal to 1. All right, and you should really write out those one-sided limits for all of our problems, but I'm going to go ahead and run through the rest of them. This next one is does not exist. From below, it's going to 1, and from above, it's going to 2. The limit as x is approaching -1, that's right here. From below, it's to negative infinity. Above, it's negative infinity, so that's going to be negative infinity. Again, AP would have does not exist. For me, I want negative infinity. And then we have as x is approaching 3, here's 3 right here. Okay, I have f of 3 is actually equal to 4, but again, I don't care about that. From below, I'm approaching 3. From above, I'm approaching 3, so that's equal to 3. And as x is approaching infinity, okay, x can also approach infinity. It can keep going forever. So if we assume that this graph keeps going, which would probably be better if it had like an arrow at the end, then this would imply that my graph, as a linear graph, would keep going up into infinity as well. Now, given use of a calculator, ultimately looking at things graphically is probably going to be often the easiest way of approaching something, although looking at the numbers on a table is also going to be useful for anything that isn't like an easy number to see. All right, so when we do things graphically, we are going to Now, for most of our purposes, looking at things graphically is probably going to be the easiest way to find a lot of our limits. Now, if the values are a weird fraction or a weird decimal, looking at a table is ultimately going to probably help you. But graphically is probably the easiest visual way of seeing it. Okay, so when we graph these, we're going to use what's called a friendly window. It's going to be the Zoom DEC window. It's not one we've used very frequently before. And if we change x and y max and mins by only multiples of the original Zoom test window, you'll maintain this friendly window. And what this friendly window does is it actually shows us some things that before you weren't able to see. All right, so let's take a look at some other examples here. Now, we actually did this first problem earlier tabularly, but let's go ahead and do this graphically as well. So let's pull out our calculator again. Let's go ahead and type that equation back in. So I have x squared minus 4 divided by x minus 2. And, okay, we can see that for our window, we again usually have a basic standard window. That's what we usually have, just like this. But again, we're going to use what's known as our DEC window. So we're going to go to Zoom decimal here, number 4. Okay, now you may notice that something that we see at the very top up here is a big open circle. I have my line that kind of goes through here, but then there's like this big space. That's what our friendly window does for us. It helps us see things like holes in our graph that we wouldn't have seen otherwise. So now this hole is a little bit high on my graph, so I want to be able to see this graph a little bit better. So again, I'm going to change my window, and I'm just going to make sure that my window is going to be at a multiple of what I already have here. So I want my y values to get a little bit bigger so that I can see better. So I can do times 2 here. That keeps it as a multiple. It will automatically change that for us. And now when I go to graph, it's still a friendly window, and boop, you can see that hole in my graph. Okay, now again, graphically, we just want to take a look at this and be like, well, where is my graph approaching as x gets closer and closer to 2? So at 2 is where that hole is. So you can see that as I approach that x value from above, it's at 4, and from below, it's also at 4. And again, you can use that table to kind of verify that as well. Our tables that you can see on this screen isn't using the right values right now because we changed that other graph before. All right, let's take a look at another example here. Let's do sine of x minus 3 times x minus 3. Oh, divided by x minus 3. All right, so let's plug that in as x is approaching 3. So clear this. Sine of x minus 3. Clear. Sine of x minus 3 divided by x minus 3. Okay, your calculator should always be in radians mode for this class. Always, always, always. There's never a situation where you should be using degrees at this point. So we want to make sure that it is in radians mode. All right, and let's go ahead and take a look at what our graph looks like. Let's go ahead and go back to our basic Zoom DEC window. Oh, there we go. Okay, so I kind of see what looks like a sine graph in here, but it's kind of like lower on this side and it goes up higher and then lower again. Okay, so the maxims, the amplitudes aren't really staying the same. Okay, I can also look at this tabularly, so we're going to go ahead and do both of that so we can verify both ways. I want to approach 3 right now, so the values I would want would be 2.9, 2.99, 2.999, 3, 3.001, 0.01, and 3.1. Okay, so I can see a table. Oops, 3. Yeah, okay. So I've got my table of values and I have my graph here. So I can see on my graph that I've got this open circle, this hole at x equals 3. Hence I have the error because the graph does not exist at that point. So it's undefined at that point. But I can see from the points around it from my table and looking at that graph that both sides seem to be approaching what value? It is approaching 1. All right, so this would equal 1 based on looking at it graphically and looking at it numerically. All right, so we're not going to do all of these problems in class, but I would encourage you to work through more of them. Go ahead and both write out my table and write out my graph for each one of these. For every single problem on this worksheet, I would like you to go ahead and graph them and also write out a table of values that approach them. All right, anything you don't finish in class is going to be part of your homework for this. All right, let's take a look at another example. Let's look at this piecewise function here. Let's do this one. All right, so when I look at this piecewise function, well, first off, you need to be able to graph piecewise functions. So, quick review on that. Remember that as this means that I want x squared plus 1 when x is less than 2 and 3x minus 1 when x is greater than 2. So to graph that, I like to put a dotted line at 2 because on each side I'm going to have different stuff going on. When x is less than 2, I want to graph x squared plus 1. So this side is going to graph x squared plus 1. And this other side here will be 3x minus 1. So this side will be 3x minus 1. Now to graph that, we could plug in points to help us do that. So if I plug in x equals 2 to this side, that would give me 4 plus 1 would be at 5. That's now at 5. When I plug in 1, that gives me 1 plus 1, which is 2. That's going to be 2 now. When I plug in 0, I get 1. When I plug in negative 1, I get 2. When I plug in negative 2, I get 5 again. Okay, so this side goes like this. And that side is strictly less than, so this is going to be an open circle right here. And then I have the 3x minus 1 on this other side, so I can plug in 2 again. 2 times 3 gives me 6 minus 1 is 5. Okay, so I have this point. This one is included, though, because it's x greater than or equal to, so that one is included. So that was an open circle, but now it's a closed circle because the other side intersects at the same place. And then I have, let's see, when x equals 3, I have 9 minus 1, which is 8. Oops. When I plug in the 3, I get 9 minus 1, which is equal to 8. So that's going to be, 8 will be like right here. So it'll be like up here. And I can keep plugging in values up. It'll keep being linear up there. So this will be approximately what my graph looks like. So I have a parabola looking side and a straight line looking side. Okay, and so now that I have that, I can again look at this graphically to see where my graph is approaching as x is approaching 2. So as x is approaching 2, I can see from this side that my y values are approaching 5. And from this side over here, I can see that my y values are also approaching 5. And so this limit is equal to 5, graphically. Now I can also do this in the calculator. Your 84s are able to plug into the calculator. It's just a little weird how it gets plugged in. Okay, so let's figure out how to plug this into a calculator. So to plug this into a calculator, let's go ahead and first put in our first equation, which is x squared plus 1. So I've got x squared plus 1. I'm putting that in parentheses. I'm going to multiply by something here. In parentheses, I'm going to write x is less than, that's less than is going to be above math, less than 2. Okay, if I just hit enter on that and I take a look at my graph, so I'm going to go ahead and go to my standard zoom for the moment just so you can see more of the graph. You'll notice that my graph kind of just stops at 2. And above that, it has that weird 0 thing because it doesn't really matter for anything over there. Okay, so that takes care of kind of the first half of my graph, and then what I'm going to do is I'm going to add on the other half. So I'm going to add to that my 3x minus 1 times this part I want when x is greater than or equal to 2. So x, second test, greater than or equal to 2, close parentheses. And now when I graph it, I have the parabola part, and then it's hard to see, but notice that this right side is no longer symmetric to the left side because it's actually linear instead of following the parabola. And so that's how you can type in piecewise functions into your calculator. Now, we were specifically interested in when this graph approaches 2. And so now that I have a graph on my calculator, I can also go ahead and change my table so that I can check that my y values are going where I want. I want it to approach 2, so I want this to be 1.9, 1.99, 1.999, 2, 2.001, 2.01, 2.1. Right, and so here we can also see from our table and also from the graph that we sketched by hand and the graph that our calculator has now given us that we do have a limit as x is approaching 5. So with any extra time now, I would encourage you to work through more of these problems. Again, you are both creating a graph and sketching that on your paper and writing this table so that you can use that to look for what value it's approaching. And with that, I would encourage you to keep working through a couple more of these practice problems, but otherwise you have the practice problems that are in the hub to work on for your homework.